No, now I'm talking. Before that, it was just people moving around. Can you hear us now? Probably not. Because now we're very loud. Okay? All right, good. So we're going to try to continue with this thing. Are there any questions, first of all? For Monday, anybody still waitlisted? Who was waitlisted on Monday? Oh, come on. All right. Have you looked at the homework yet? Bad. Very bad. It's big, and there are two of them before you get to the actual quiz. That's part of your grade.
And that's due next week, right?
Yeah. But again, that's a lot of work. Okay, so I'll try to do this. I'm going to do a mixture of whatever this thing is. It's a little PowerPoint that's kind of silly. And then I'll jump on my, where I'm actually going to write. Okay, so as we agreed on Monday, algebra is about solving equations. And when you look at equations with more than one variable, the only way we can solve it is to graph it. And that's what the graph is. A graph of an equation is actually a solution to that equation, but there's no other way we can solve one. Okay? Did we kind of talk about how you cannot list all the possible answers?
Yeah.
And so, an example. Let me try something. So this is probably as loud as it can get at this point, and crank up your speakers. Can you guys hear this better now? Same here. Oh well. So graphs are solutions to equations with two variables. So if we look at this example right here, if I'll put this problem on the board, 2x plus 3y equals 18. Can we find some solutions to this equation? So meaning we're looking for values for x and y that satisfy this equation. Can you give me some values for x and y that will make this work?
4 and 3.
4 and 3, let's
3
try.
3 for x and 4 for y.
Okay, so 3 and 4.
Yeah, I mean 3 and 4.
Oh yes, I think I am muted. Let me try this.
Oh, you just...
Okay, I think now I'm unmuted. Can you guys hear this better? Thank you for catching that. We'll get a hold of this thing. It was a complete disaster at 1 o'clock today. This is a little better. But anyways, what were you saying? 3 and 4?
Yeah, 3.
Okay, so ordered pair as an x equals 3 and y equals 4, right? And the way you check that, you plug this in, 3 for x, 4 for y. Is that going to work? 2 times 3 plus 3 times 4. So what is that? 6 plus 12?
Yeah.
So this does equal 18, so check. So this would be one of the solutions. Can you give me another one? Or are we done? Are there more? -3 and -4 will give me -18. Actually, so that won't really work.
6 and 2.
6 and 2, let's try that one. If we do, I'll write it over here. Maybe over here. 6 and 2. If I plug in 6 for x and 2 for y, what do I get?
12 plus 6.
I'll get 2 times 6 plus 3 times 2, so that's 12 plus 6 equals 18. That checks. Okay, so that's 2. I can do many more, and there's no way I can list them, so the only way I can express this solution is to kind of graph all possible pairs. So that's what the graphing comes in. All right, that's why we need graphing. We need graphing in order to express the solutions. So at this point, I will be sharing my desktop with the online group, and we'll see how that's going to work out. And why is it all shaking right now? Okay, so I'm sharing my desktop. So I'm going to pull this out. Let me do something here. All right, so the equation was 2x plus 3y equals 18. And we found 2 solutions so far. Which are, what were they?
3 and 4 and 6 and 2.
3 and 4, 6 and 2. So we can graph them, right? So we all know where those points live. We can do is we have our x-axis, we have our y-axis, and 1, 2, 3, 1, 2, 3, 4 is somewhere here, and 6 would be where is it? 6 and 2 is somewhere here. So if I do that, every point on that line solves that equation. That's what graphs are. Okay, it doesn't have to be just a straight line. Depending on your equation, you might get something curly or curvy, rather. But what that means, I can ask you this. Let's say this point right here, whatever that is that going to solve our equation? No, it's not part of the solution, which is the graph. And if I grab this point right here, will that solve our equation?
Yes.
Yeah, because it's on the line. Now, when we're looking for the graphs, there are a few points that are easy to find, and those points are the y-intercept, if I let this axis go further, and the x-intercept. Okay, so this right here would be the x-intercept, and this right there would be the y-intercept. Now, if you think about this, all y-intercepts, whatever they are, if you have a crazy-looking graph that hits the y-axis at many, many points, all those points along the y-axis have one thing in common. What is the x-coordinate of which one of those points? 0. So in order to find the y-intercept, you just have to set x equal to 0 and solve for y. So that's what we're going to write down, that in order to find we will set x equal to 0, and solve for y. Is that okay? So that's really easy to do. Now at the same time, if I look at the x-intercept, all those points have another thing in common. They have what value for y? And y is 0. So in order to find the x-intercept, we'll set y equal to 0. So we'll set y equal to 0 and solve for x. Is that okay? Just a quick review of that. So going back to our equation, now those two are 2x plus 3y equals 18. If I just ask you, can you find the x and y intercepts? What are they? Y is 6. X is 9, so 9, 0. And the really easy way to do that, let me try something fun here. Oh, let me, color it. Okay, here we go. Paint. Here we go. So I'll do this. Really what you're doing is just get rid of the x's and solve for y, so that's 6, right? And then cover the y's and solve for x. So that's one way of looking. Is that right? Well, unless you don't have a paint can option, then you're in a bit of a trouble. All right, let me see what those guys are saying. They cannot hear us. Yeah, it's a little quiet, but I gotta turn the volume up. Gets a little better. Okay, so having those 2 points, you can just grab the line. So this one right here was, what was that? 0, 6. And this one right there, not drawn to scale by no means, 9 and 0. Okay? Now, so this is all fun and kind of, a little silly, because of course we're going to treat the lines a little differently. We've done it before with the slopes and such. We'll get back to that. It's just to kind of reintroduce this whole graphing idea. By the way, what is this whole thing called? The y-axis and the x-axis put together. What's the name for that thing? What? Yeah, coordinate plane. That's what it's called. Sometimes it's called Cartesian plane. You can use that name. I had a student who called it Kardashian plane. Well, that's, that happens too. But it's a Cartesian plane or coordinate plane. Okay. Now let's talk about points on the plane. So points on the plane. The first thing that we want to talk about is finding the distance between 2 points. On the plane. So basically we're going to try to derive the distance formula. So let's say if I have 2 random points, let's call this point x1, y1, and I have some other points, let's call that point x2, y2. And I want to find the length in between those 2 points. So I'm looking for the distance, so I'm looking for the length of this segment, let's call it d. So we're looking for d. How many of you know how to do that? Well, that would be the slope of that line. I'm not looking for the slope. I'm looking for the actual length.
A squared plus b squared plus c squared.
Very good. We're going to use the Pythagorean theorem. Let me just ask this question. Right, we're going to utilize the Pythagorean theorem here because I can actually think of this as a little triangle. And it is a right triangle. And we know the Pythagorean theorem states if I take one side square that plus another side square that, I'll get the square of the hypotenuse. Right? So all I need to know really is the length of this side and the length of that side. Now this side is just a horizontal, it's a vertical line that is in between two values that are y1 and y2. So for example, if y2 was hypothetically 6 and y1 was hypothetically 3, what would that length be? 3. You just go 6 minus 3, so that's this length right here is y2 minus y1. Well, what would be that other length?
X2 minus
X2 minus x. So then by Pythagorean theorem, d squared equals y2 minus 1 squared plus x2 minus x1 squared using the Pythagorean theorem. And therefore d is the square root of all that. So that's the distance one. So I can actually use this distance formula to find the distance between these 2 points we used earlier, 3, 4, and 6, 2. Or actually, let's do Let's do 6, 2, and 9, 0. That's what I want to do first. I want to do this example. Find the distance between points 6, 2, and 9, 0. Just use the formula. Okay? It tells me to subtract the y values and square them, square that difference, and plus subtract the x values and square that difference. So what are we going to end up with? What?
13.
Right, under the radical. So it's still negative 2 squared plus 3 squared. So square root of 4 plus 9. So square root of 13. That's right. So that's the distance between those 2 points. Whatever the square root of 13 is, I don't really care at this point numerically. That's a perfectly good.
You don't need the square root on the second to last part, like before or before 9, do you? So you already square rooted it, negative 2 squared, 3 squared, 3 squared root of it, so you don't need it on the second part of before the plus 9.
No, but I squared those, but I didn't square root them yet. So 2 turn.
Oh, never mind.
Yeah. So that's 13. Is that okay? Questions on that? Seen that before? Nice and friendly? All right, good. Now let me do it a little bit. Let me do something else. I'm going to ask you this question. Are points 6, 2, 9, 9, 0, and let's say negative 3, 8 collinear. Meaning they're all on the same line, right? Now there are two ways of doing that. There's a really easy way of doing that, because you already know that 6, 2, and 9, 0, they from that original line that I wrote, right? So the only thing we really need to check whether negative 3 and 8 satisfy that original equation. And if it does, then they're on the same line, right? But let's say we didn't know about the equation. This is the question that I'm asking you, let's say on the homework or on the test, and there are no previous information about any equation so far. So it's just 3 random points. And my question to you, are they on the same line? Does the question make sense? So one thing that you cannot do is just to go, well, here's the first one, here's the second one, here's the third one, and they look on the same line, so they're collinear, not good enough. All right? Another thing that you cannot do is here's the first point, here's the second point, here's the third point. They do not look to be on the same line, therefore they're not collinear. So you cannot do this by just graphing. Is that okay? So we have to do some extra work. Now let's talk about this. If these 3 points were collinear, so let's say you have 3 points that are on the same line. Well, we can compute the distance between these 2 points, right? Let's call it distance 1. And we can compute the distance between these 2 points. Let's call it distance 2. And we can compute the distance between these 2 points. Let's call it distance 3, whatever. Now, if these points are on the same line, what can you say about D1, D2, and D3?
D1 plus D2 equals D3.
That's right. In order for them to be on the same line, the sum of the smaller distances has to equal the larger one. Otherwise, you're going to end up with a triangle, and with a triangle, the sum of 2 sides is always greater than the third side. Okay? So that's what we can check. We can actually compute the distance between each pair of the points and then see whether that's going to balance out. Does the plan make sense? The good news, we already did one distance. We already computed the distance between 6, 2, and 9, 0, right? The bad news, we got square root of 13. So we're going to be adding square roots and stuff. So that's not going to be fun. But let's try. Are you with me? Yeah?
One question on that.
Go ahead.
On the top part, aren't you supposed to do square rooting before you add? So the square root of 4 plus 9, shouldn't you have done square root of 4 plus the square root of 9?
No, the other way.
Yeah, I was thinking.
Yeah, this is really, think of this as set of parentheses. So you do what's under the radical first,
Okay.
and then you do the outside side. So the square root does not distribute through the plus, okay? Otherwise, the life would be too perfect, and we'll just have our, let's do it. 1 second. They all lost sound. I don't know what's going on with our mic. Our mic is dying on us. We need to get a new mic. We're going to start a fund. Mic money. I'll be doing this a lot because the guys are asking questions. And, they just went to this new conference system, and it's in the beta version, and it's just a nightmare. They used to have a different product that you had to pay money for, and it worked well. Now they got some piece of crap for free, and we're dealing with this. You know, I shouldn't be cursing because I'm recording myself. But apparently, all they're getting is static. So that's upsetting. Sorry. Right now I feel better. Because I know it's frustrating for you, for them, for me as well. So anyways, we already computed, let's call this distance 1, which is the distance between 6, 2, and 9, 0, and we got D1 to equal to the square root of 13. So we did that before. Okay? well, let me call d2 would be the distance between negative 3, 8 and 6, 2. So let's use that same distance formula. So d2 equals the square root. So I'm going to take the y values. Again, in any order, in which order you subtract, doesn't matter here because we're squaring it. The only difference between 8 minus 2 and 2 minus 8 is the sign, right? You either get a 6 or negative 6. But you're going to square it, so it's 36 either way. So that doesn't matter. And same thing with the axis, so that's 6 minus negative 3 squared. So negative 6 squared plus 6 minus negative 3 is 9. 9 squared. Is that right?
Yeah.
So square root of 36 plus 81. So what does that equal to?
17.
Is that right?
Mm-hmm.
Things getting nasty. We have to be adding square root of 13 to square root of 117. That's going to be interesting. Of course, without the use of a calculator, that's going to throw us off.
So how did you know to use 6, 2 instead of 9, 0?
Oh, you could have used 9, 0. Doesn't matter.
Okay.
Basically, you would get one number larger than the other two, so you just make sure that the two smallest one add up to the big one.
Gotcha.
In any order, It's just I knew beforehand that these 2 points are closer than the other two.
Right.
But if you did the other pair, it would still work. And that's what I'm going to do next. I'm going to do the other pair. And let's call it d3, which is the distance between negative 3 and 8 and 9 and 0. So again, using the same old distance formula, I would have to subtract the x values, the y values, and again, it doesn't matter in which order you do those, it'll work out. Because they're all squared and there's a plus in the middle. So everything is nice and friendly. So, we're ending up with negative 8 squared plus 12 squared equals to what? Square root of 64 plus
144.
140. Are you sure?
Yeah, I'm sure.
Yeah, that looks good. And what is that?
12
squared.
208? Yeah, I think that's right. 208. Okay? So we just computed 3 distances. So the question is, if you take square root of 13 and you add square root of 117, will that equal to the square root of 208? And this is not a trivial thing to us. It's not obvious. If one number came out to be 2 and the other one came out to be 4 and the third one came out to be 6, then we're good, right? But here it's a little tricky. But let's talk about square roots. Because there is a way to simplify square roots. We all know how to take square roots of perfect squares, like square root of 16 is 4 and blah, 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 right? But if I ask you something like this, quick example, a square root of 8. 8 is not a perfect square, but can you still simplify?
Yeah.
Yeah. You can break 8 into a product of a perfect square and something else, which is 4 and a 2. You can think of square root of 8 as square root of 4 times 2, and then you can take square root of 4. What is the square root of 4?
2.
So it becomes 2 square roots of 2. So square root of 8 is that. So I can try and do the same thing here. we should be a little harder because 117 is kind of a nasty number, right? So I'm probably going to have to do some kind of a factorization of 117. Do we know that it's divisible by, let's say, 3 really fast? We know that, right? How do we know that?
120 minus 3.
Keep talking.
That was me.
Oh, that were you? Okay.
120, 3 divided by 120 is 40, so 3 times 3.
Very good. You can do it that way. So what did you get? 3 times 39. Well, 39 is clearly divisible by 3, right?
Mm-hmm.
What is 39 equal to? 3 times 13? So this whole thing is really 9 times 13, where 9 is a perfect square, right? So that's a good thing. Now I'm just going to take a wild guess, but we can do the same thing with 208,
52 and 4.
52 and 4, and 52 is still divisible by 4. That's a deck of cards. 13. 13 of them, right? You have 4 suits, 13 cards, from ace to king, right? 52 in the deck. You got to know your 52, 13 times 4 thing. It's cards. It's a deck of cards, right? Anyway, so good. This one will break down into 16 times 13. So really, this whole problem is square root of 13 plus square root of 9 times 13. Will that equal to square root of 16 times 13? Well, square root of 9 will turn into 3. And a square root of 16 will turn into 4. So all we have is square root of 13 plus 3 square roots of 13. That does it equal to 4 square roots of 13? Yeah, so it's check. So they're all collinear. So we got it to check. 2 smaller distances added out to the bigger one. How those guys put it. I mean, I have to, yeah, I'm going to type this.
Yeah, you got 2.
Yeah, I know, we have to fix the mic. Now, for those of you who are here, I'll go back. Is that how you spell Ben?
Yeah.
Yeah,
It's good now.
Can't be.
That's right.
No.
I think that was it.
Yeah, I think it's right.
Really, Ben Weirdly?
Yeah.
No, it can't be Ben Weird.
There's a D
There's
before
a
IDT.
Oh,
What?
IDTH. WID.
IDT, like that.
Yeah.
Weird.
no, we got that right.
All right. So that was fun?
Yeah.
Yeah. By the way, I really like the way you think. That's good. I can sign a piece of paper of yours right now. Okay. Well, after class. Okay. Okay, so distance formula, good. You need that. It'll show up in just random places as we go along. That's why I'm spending time on it. Most of you know this. Some of you getting bored for, I don't know why, because it's so much fun. The midpoint formula, that's another one. We'll need that. The midpoint formula, well, it just does exactly what it sounds like it should do. Given 2 points, it will find the one that's exactly in between. The dead center between those two other points. So the way we find that midpoint, again, if you have one little guy and then another little guy, then the midpoint is somewhere in between. Is that close enough? Close enough. Close enough. Okay. They're gonna put them in. So all we really have to do, this is the easy formula. All we really have to do in order to find it is to average our x values and average our y values, right? The y coordinate would be just, the average of these two values. So you add them and you divide by 2. And the same thing with the x's. You add them and you divide by 2. So the average. So the midpoint formula is pretty nice and friendly. It's just x1 plus x2 over 2 and y1 plus y2 over 2. Okay, the average of it. And it's really easy to use. If I grab any pair of those points that we just played with, -3 and 8, and let's say, what was that one? 3 and a 4. And I can ask you, where's the midpoint in between? So all I have to do is to average the x's, so -3 plus 3 over 2, right? And average the y's, 8 plus 4 over 2. So what is the x coordinate?
0.
X coordinate happens to be 0, and the y coordinate
6.
6. Actually, we just kind of found our y-intercept without really, looking for it. It just showed up. Oh. 0, 6. Any questions on these two little formulas? Good. All right. So the next thing, they'll come back today. So don't give up on them yet. You'll see this too later today, but let's talk about circles. If I ask you, what is a circle? What will you say?
Round.
Round. Well, my face is round. Does not make it a circle, right? Oh, it's roundish. I don't know what round means. What is round? Yeah.
Circles mean distance from the center.
I like that. Yeah, so it's a collection of all points in the plane. I'm just trying to see if there's a way to turn the mic on. Anyways, so yes, the circle is the set of all points in the plane that are equidistant from some other fixed point that we call a center. Kind of a weird definition, but that's all it is. You have a center, and all points that are same distance from that center will form a circle. So distance creeps in. Okay. So your book has a definition of a circle somewhere in there. Let's see, because I don't want to write that big sentence. Y-intercepts, we talked about them, blah, blah, blah. Lines, parabolas, yeah, here we go. Here's a nice definition. Don't read the second part, but the real definition here is this. So, a circle is the set of all the points in a plane that are fixed distance r, the radius, from some center. Don't look at this yet. We don't know what that means. So they just decided to use the letters H and K. Let me answer that. Center H and K. So somehow this should give us this little formula. So if I graph this, so let's say here's that point H and K, and then I have a circle that is around it. So the distance from that center to any point on the circle stays fixed. And that distance, we're going to call the distance r. So if I take any arbitrary point on that circle, let's say I'm going to graph this point, and I'll call it xy. What is the distance between hk and xy? R, right? So if I plug it all in into my formula, I can say that r equals the square root of x minus h squared plus y minus k squared. The change in x squared, the change in y squared. Again, the order, the way I wrote it doesn't matter, so here we go. Now, square root is always an ugly thing, so I'm going to get rid of the square root. I'm going to get rid of that square root by squaring the both sides of this equation. So that will give you r squared equals x minus h squared plus y minus k squared. And that's the equation of a circle that is centered at the hk and has a radius r. Okay? So this is equation Is that right? So we kind of use the distance formula to derive it really fast. It's kind of silly. So circle, equation of a circle is nothing but a distance formula. That's all it is. Okay, where the numbers h and k would represent the center of that circle. So let me do an example. I'm going to write something on the board. And you will answer two questions. Well, three questions. First question, are we looking at a circle? And if yes, then state the center and the radius. Does that make sense? So I'm going to write something. So is this a circle? And if yes, state the radius and center. So I'm going to write this. X minus 1 squared plus y plus 2 squared equals 4. And basically all we have to do, we're trying to match with x minus h squared plus y minus k squared equals r squared. So you're just trying to match the equation that I gave you with the equation of the circle. Yeah.
There's a circle and radius is 2.
That's right. It is a circle. It kind of fits this model. There are really two things that you're looking for that will throw you away from a circle. The number on the right side has to be positive. If that number is negative, then there's no way it could be a square of something. Right? The way it's written, r squared should be positive. The negative radius doesn't make sense to begin with. Right? So if I write something and that number is negative, then I'm messing with it. And another big thing is a plus in between the parentheses. Okay? If I throw in a negative, then it's no longer a circle, it's some other crazy looking thing. It's called a hyperbola, something like that. Well, we might talk about it later. So yes, it is a circle, and you're absolutely right. The radius of that circle is 2, because the radius is something that is being squared over there. So if r squared equals 4, then radius equals 2. Okay? So good. So yes, a circle. Radius equals 2. What is the center? So you just have to identify the values of h and k. What is h? So 1 or negative 1?
1.
So you're right, you're just going to match literally x with x. Minus is there, so therefore h is 1. Right? Because minus is already there. So 1 is the x coordinate of the center. What about the y coordinate?
Negative 2.
Negative 2. Good. So basically, if you just remember to take the opposite side of whatever is written, you'll be fine. Because you have a plus 2, but it has to be a minus. So you think of y plus 2 as y minus negative 2 squared. So k is negative 2. So that's right. The center is 1, negative 2. Okay? Having these two things, the center and the radius, we can roughly do a sketch of that circle. We actually can do a pretty good job at sketching that circle. So does that make sense how we read that information? Okay. No? Good. All right. Let's try another one. What if I do x squared plus y plus 3 squared equals 5? Do you see the center? First, was that a circle?
Yes.
Yes. Number on the right is positive. The sign in between parentheses is positive. So yeah, it's a circle. What is the center of that circle? 0 and negative 3. Very good, because there's nothing subtracted from x, so there's a silent 0. So that means it's sitting somewhere on the y-axis. Okay? Now, what is the radius?
Square root of 5.
Square root of 5. Very good. Because again, keep in mind that the number on the right is already squared. Square of something. In order to get 5 from squaring, you have to be squaring the square root of 5. Is that all right? Does that make sense? Can ask you to go backwards. Can ask you to find the equation of a circle. That is centered at negative 2, 4, and has a radius of. So, given the center and the radius, can we find the actual equation of that circle? What do I need to write?
In parentheses x plus 2 squared
Good.
plus
Y minus 4 squared equals 3.
equals 9.
Equals 9, right? R equals 3. So remember how we put R squared there, so it's 3 squared. Is that okay? Any questions? Have you done that before? You've done circles before. But, you know, they'll come back, hopefully. Here's the very famous, the most famous circle. The celebrity among circles is this guy, x squared plus y squared equals 1. What is the center of that circle?
0.
0, 0. So the center of the origin, what is the radius? 1. It's called the unit circle. You used it a lot in trigonometry and basically everywhere from there on. It's a circle that's centered at origin. So it's 0, 0. Sure. Or previous page. I don't know what the question. Okay. All right, good. So let's take a quick break. You know, maybe 10 minutes or so, and then we'll continue while I'll chat a little bit with the online guys. Okay, so let's continue this thing. With my so same question. Is this a circle with yes, center and the radius? Or similar question. So let me throw some like this thing. Again, is this a circle? Same radius and center. So let's look at something like this. X squared minus 4y plus 7 plus 2x plus x squared equals 8. Now again, we're trying to match with the original equation. If you can match the expression that I just wrote with the actual equation of a circle, then we're in business. We're looking at this circle, and we'll be able to state the center and the radius and all that good stuff. Because from what it looks like, it doesn't look like a circle right now. What does it? What do you think?
Could you combine
Combine what?
some other terms?
Well, let's try. And then I forgot to do the whole assignment because we have to do this in the first few days, and then we'll stop. I'll remember that. Well, what are the like terms there? What can I combine? Actually, you're right. I made a mistake. You're absolutely right. Let's make it y squared.
Oh man.
Yeah.
I'm lost.
But you're right. We could have combined x squares, but let's say it's a y square. So yes, there's nothing to combine. But well, let me ask you this. You have seen this before, I hope, in your other math courses where you were asked to take things like, let's say, x squared plus 2x, and then do some voodoo to make, oh yes, it is a very technical term. Do some voodoo and then get it to look like that with some number in there, whatever. Okay? Remember that you had a square of an x and then x that's not being squared, and all of a sudden you packed it all inside one square. You had a square that's kind of broken, and then you're trying to make it into a square that's not broken. There's a word that, there's the process that turns.
Distributing it.
What?
Distributing it.
Well,
Balancing the equation back.
well, okay, but if I try to factor x squared plus 2x, right, I'm just looking at the x's. If I try to factor that, I'll just get this, right, that's me factoring. But it's not something squared, right? This does not make me happy. What? Completing the square. That's what I want to do. I want to complete the square. Very good. Well, now let's see how well we remember that. Because completing the square will show up here in a few other places. There will be a few topics that require us the knowledge of how to complete the square. So the way I'm going to do this problem, I'm going to first, I see that lonely 7, I really don't care about that 7, I'm going to subtract it to the other side. I'll subtract that 7 to the other side. And I'm also going to rearrange the terms so I have this, the x's first. And I'm going to leave a little gap. And then I'm going to write the y's after that. And then I'm going to leave a little gap, and all equals to 1, right? Because 8 minus 7. Is that okay?
Yeah. I have 2x on top.
You're right. Thank you. Let me do something. I don't like where I wrote it. I'm like those dudes on CNN moving things around. Now, do you remember how to complete the square? Good. What do I need to do?
Divide that by 2.
Very good.
Square it.
2 by 2 and square that. So what is that?
1.
1. So I'm going to go ahead and add 1 over here, right?
And then you do it to the other side.
I have to do it to the others because, well, if I add a number to one side of an equality, I have to add that number to the other side of that equality. So plus 1. Very good. Now I have to do the same thing for the y's. So I will take, guide me through it. I'll take the 4.
Is it negative 4?
It doesn't matter because I'm going to square it.
4 over 4.
4 over 2. It's always the 2. That's the thing. 4 over 2. But nice pattern recognition. I like that as well. So what am I adding?
2.
Squared.
4 squared.
4. So I'm going to add 4 to this side, and I'm going to add 4 to that side to keep it balanced.
So you said it doesn't matter if it's a negative or not.
Well, the only time when it matters, basically this sign will determine the sign inside the parentheses.
Right.
This sign will determine the sign inside the parentheses. So I know the x will have a plus inside and the y will have a minus. That's the only time where it matters. It doesn't matter in the actual completing the square process. Well, now I'm going to try to do some factoring. We kind of know that x squared plus 2x plus 1 is a perfect square, right? What is it? What goes on the inside? X plus 1, right? Even if you didn't know that, if you try to factor two numbers that multiply to 1 and add to 2, 1 and 1. So you have x plus 1 times x plus 1, x plus 1 squared. Right? How about the second parenthesis? Y squared minus 2, very good, equals 6. So by completing the square, we got this we're able to pack all the variables inside the squares and only have a positive constant on the outside. So now it clearly looks like a circle, does it? What is the center of the circle?
Negative 4.
And the radius? Square root of 6, right? Okay. There are some very, very terrifying looks that I'm receiving right now. How many of you have done completing the square? How many of you have no idea what I did? Which is okay, because I'll talk about it. That's important. Do I need to talk about this? Okay, good. You and I, we did completing the square. Well, it's like a year ago. Well, a little less. It was at the end of that semester. Okay, completing the square. So let me talk about this in a little greater detail. Okay? So completing the square. I'm going to do something silly first, if you don't mind. Let's say I have... Okay, well, why do we... By the way, don't write this down. Could you verbalize this statement? Could you read it to me? 5 squared. Why do we say it's 5 squared, not 5 chairs, not 5 trash cans? Why is it 5 squared? What the hell?
2 different parts that go together.
Yeah, because we connected to the area of a geometrical shape that's called a square. In order to find the area of a square, that, let's say, has the length of each side is 5, then the area is 5 times 5, 5 to the power 2, but since it's so closely related to the square, we just said 5 squared. Okay? This is why 5 to the power 3 I read it as 5 cubed, because that will represent the volume of a cube. Which side do I need? Okay. Right? So that's where the language comes from. So there is a connection between our algebraic expressions and actual geometry. So what I'm going to play with now is a little geometry game. I'm going to draw a square. Actually, I do have this. I can draw a square. Okay. And let's say the length of the side of this square is A, so A. Let me take it back. How about X and X? That will be better, because we're already dealing with X's. Okay? So I have a square, and then I'm going to draw a little triangle. Did I say triangle? Oh, I totally meant a rectangle. Sorry about that. Well, I'm going to take this rectangle, and I'm going to call this side B. And I worked really, really hard, so that side is still X. By construction. Not by picture, by construction. Okay? Now what I'm going to do, I'm going to cut this rectangle in two. Can I do that? And cut it by exact half. I'm just playing. Okay? Who is me right now? I should have brought props, but that's good enough. So I'm going to do this. Now, I'm going to cut it in a very weird way. So let's say after I cut it, oops. How do I shrink this thing? Oh, that's not right. Okay, well, I'm going to build a few extra ones. I'm going to build, oh, no. Yeah, go back. Okay, so let's say I cut that one in half, so it looks a whole lot skinnier now. So it will sound like that. So that's one half of it. And I'm going to take another half. This is fun. Copy. I'm going to put that other half here. And then I'm going to, oh, come on. I'm going to turn it. Turn. And then I'll move it over here. Oh, that's awesome. Look at that. So that original B by X, I cut it in half and I placed it in as such. Now let me ask you this. If the original side was B and I cut it in half, what is the length of that side? B over 2. And what is the length of this side? B over 2, right? Now this shape that you see in front of you, what kind of shape is that? It's weird, right? It's not a geometrical shape that we know, but it's very close to a square. You see that? There is one thing missing. What's missing? How can I complete the square? That little corner, right? What is that corner? What kind of shape of that corner? It's a square, right? I can actually take, since I'm geeking out already, I will take and make a little square right here. Right? That little piece, I needed that to literally complete that square. We do that in math a lot. We call things the way we see that because we have very little imagination. We say complete the square. Can you tell me the dimensions of that square? What is the size? What are the sides? B over 2 by B over 2. So that was that missing piece. Take the B, divide by 2, and square that. Because look, if I do this, what is the area of this one large square right here? X squared. And what is the area of this rectangle right there? X times B over 2, right? What is the area of this rectangle over here? X times B over 2. And what is the area of that little square? B over 2 squared. And what is the area of this big square?
X plus b over 2 squared all over 2 squared.
Right, so therefore x plus b over 2 squared equals to all the parts. X squared plus b over 2x plus b over 2x. So that's 2b's over 2. So that gives me that rectangle back, the one that I was cutting. So that's just bx plus b over 2 squared. So that's where that whole thing comes from. You're taking the number in the middle, you're dividing it by 2, and you're squaring. That's that missing bit. And b over 2 goes in there. Well, that was a fun way to look at it, isn't it?
Yeah.
Have you seen that before? That's kind of huge. Because we all know this formula. The a plus b squared equals a squared plus 2ab plus b squared, right? So here's that 2. That's another reason why we divide the middle term by 2. Because a is playing the role of the x. 2 is 2, so the only thing that's missing is that. By the way, this b is different from that b, just a coincidence. But anyway, so keep that in mind. This is completing the square. So we take the term that's next to x, we half it, and we square it. So that gives us that little, tiny little bit, the one that we're missing. Oh, I'm getting some questions. Thing. Oh yeah, it's totally possible that it's our internet. Our internet is horrible here. Right? Have you guys noticed that if you live in the dorms? Okay, so that's what that whole division by 2 comes from. All right, remember that from a year ago or so? Okay, good. So let's do another one. Let's do another problem. Another example. We can just make one up. We can throw fractions in there. Do we need that for the full enjoyment? No fractions?
No fractions.
Okay, no fractions. X squared minus 5y plus y squared minus 6x plus 1 equals 7. Okay. So again, we're back on the circle thing. So we realize in order to do this problem, we have to try and complete that square and so forth. So remember the steps that we took. We first got rid of the constant. So we first got rid of that constant. And then we rearrange things. And so x is with x and y is with y. So x squared minus 6x. You're going to leave a little gap plus y squared minus 5y equals 6. Okay? So let's try and complete the square. What do we do for the x's? What is missing in order to complete the x's? Oh, come on, we just do that. What do? What?
Break apart 6x.
Well, yeah, so what am I going to do with that 6? Divide by 2, square that. So what am I adding? 9. I'm going to go ahead and add 9. I'm going to add 9 to both sides. Now I'm going to do something similar to the 5. Right? So 5 divided by 2. And square that. So what's that?
2.5 squared.
Yeah. Or stick with a fraction, that's easier. How do you square 5 halves? What is that?
5.
25 over 4. You square both. Fractions are good for you. Convert them to them decimals. Decimals are bad. Well, I've told you no fractions, so I lied. I do that. Okay. So adding the fraction to both sides, oh well. Alright? So now, the left-hand side is just x minus 3 squared, right? Because again, you always go for this number before you square it. The way we got, you see how b over 2 squared over there, but inside the parentheses is just b over 2 before squared. So that's why we're just putting a 3 on the inside. What are we going to put next to y? Pi over 2. So whatever that was before squared. Well, on the right side is 15, right? 6 plus 9 is 15, plus 25 over 4. I need the common denominator, which is 4. I need to turn 15 into... Oh, good. That's the answer. Very good. So yes, the answer is 85 over 4. So we're going to turn 15 into 60 over 4, and you add them. So yes, 85 over 4. Very good. Whew. So it's a little fraction. Oh well. What is the center of that circle? What is the center? 3. And 5 over 2. What is the radius?
85 fourths.
Square root, right? So it's a square root of 85 over 4. It's politically incorrect to have a square root in the denominator, but it's a 4, so we can deal with that really fast. So it's a square root of 85 over 2. And I can do that. Now 85. Is that anything nice? 85 divisible by 5, 17 times 5, is that right? So yeah, that's nothing you can do. So that's the radius. Whatever that is numerically, I don't care. And neither should you. That's your answer. Don't plug it in the calculator. Well, when you work on your My Math Lab, they'll actually ask you. Either give it an exact answer, which is square roots, or compute it to like 4 decimal places, or 2 decimal places, so then follow that. When we're going to be doing exams, I really don't care. That's yours. Okay, good. Are you enjoying the circles? No? Oh, come on. This is the most fun we're going to have this whole semester. Because I'm going to start being all serious starting next week. We're actually going to learn hard stuff. So here's an example. So let's say points -3, 4, and let's say 1 and -2. So these 2 points, they are endpoints of the diameter of the circle. Do you understand what that means? What a diameter is? So it goes from one end to the other end through the center. So these are the 2 endpoints. So if I graph it, -3, that's too many, 1, 2, 3, 4. +4, and then 1, -2. So that's the, let's say that's a circle, whatever. So that's the diameter. These 2 are endpoints of the diameter. Can we find the equation of that circle? Find the equation of the circle. So in order for us to find the equation of the circle, we need to have 2 things. One is the center, and the other one is the radius. Or radius squared. If I just know the radius squared, go ahead.
Wouldn't you use the midpoint formula to find the center?
Sure. Because we realize that the midpoint, I mean the center lies right on the diameter and should be right in the middle. So we will use the midpoint formula to find the center of that circle. Very good. So we'll do that. Use the midpoint formula to find the center. So So the center would be, we will take the sum of our x values, so it's negative 3 plus 1 over 2, right? And the y values, 4 plus negative 2 over 2. So what is the center? Well, it's negative 2 over 2. So it's negative 1 and 1. Right? So it's negative 2 over 2, positive 2. So that's the center. Good. So we use that midpoint formula to find the center. So far, we have this. We have x plus 1 squared plus y minus 1 squared equals r squared. Okay? How to find that r? Sure. I can use the distance formula. Distance between what and what?
Midpoint and one of the endpoints.
That's right. I can use the distance formula to find the distance between the center and any one of those endpoints. That'll give me the radius. Or I can do it even faster. Since this is potentially soon to be equation for that circle, then every point on that circle has to satisfy that equation. So if I take one of the endpoints, let's say 1 and negative 2, and I just plug it in for x and y, it will just give me r squared for free. You see that? Because that's what an equation is. It has to every point on the graph has to satisfy that equation. This graph is a solution. So if I know that these 2 points, either one of them, they solve this equation, and I can plug in the x value, the y value, and the r squared will come out. Does that make sense? So I'll just grab, doesn't matter, first point, just using negative 3 and a 4, we'll take negative 3 plus 1 squared, 4 minus 1 squared equals r squared. Right? So what do we get? Negative 2 squared is 4. 3 squared is 9, so that's 13. So that's the r squared. R squared equals 13. So then the equation itself of this circle is x plus 1 squared, y minus 1 squared equals 13. Does that make sense? We'll use the distance formula. But I mean, the equation of a circle is the distance formula, so it's same. That's exactly what the distance formula will produce. Okay, good. So that's kind of, I think we just got too happy with the circles. Maybe I did. They're fun. Some of you tend to disagree, but that's all right. Okay, so let's go on. So I want to talk a little bit about functions before we leave, because I want to stop at the same place where I stopped with the earlier section. I don't want us to get too far ahead. But so functions. That's what that's kind of a big deal in algebra and the math in general. So before we define a function, we'll define a relation. Here's a fancy term, relation. And the way I think of the relation is just a set of ordered pairs. That's it. That's the definition, a set of ordered pairs. Okay? So I'm just going to give you an example of a relation. So since it's a set, So let's say, call it R equals to, and then I'm just going to put a bunch of ordered pairs in there. So really doesn't matter what. 1, 2, 6, 8, 1, -2. With the earlier class, for some reason, we also had a monkey and a cheese. That was another pair that we used, monkey and cheese. That happened. I know those guys. Okay, they can hear me. See that? They're laughing. They can hear me. Okay, so what this says, that somehow 1 relates to 2. I don't know why it just says that. 1 relates to 2. Ordered pair 1, 2 means 1 relates to 2. 6 relates to 8. 1 relates to -2. Monkey relates to piece of cheese. But not the other way around. Cheese does not relate to monkey. Or 8 does not relate to 6. It has to be in order. So in order for me to say that number 1 relates to number 2, it has to have an order pair of 1, 2. If I want to say 2 relates to 1, I need to have that. That says 2 relates to 1. Okay? Because again, relations is a pretty wide, it has a very wide definition. So here's one way to relate one number to the other. Let's say one number relates to the other if the first number divides the second number. So 3 and a 6. 3 relates to 6, because 3 divides 6. Is that okay? 2 and a 10. 2 relates to 10, because 2 divides 10. But 10 does not divide 2, so 10 does not relate to 2. So it does not have to be a two-way street. Is that okay? Just a minor note. So one way to express this relation, I can say that, well, number 1 relates to number 2. So I can just say that little arrow pointing from 1 to 2. I can say that 6 relates to 8. I can say that a monkey relates to a piece of cheese. And what else do I have? I have 1 relating to -2. Okay? So that's kind of a visual way to represent this relation. So it's one-way arrow, goes from here to there. It's not a two-way thing. Now, the set on the left by itself, these elements on the left, we call that domain. So basically the set of all the x values, the set of all first numbers in each, or elements in each ordered pair is called the domain, while the second part is called the range of the relation. So where you start as domain, where you end up as the range. And again, you've seen those terms before, I'm sure. And we'll dig into that. So I can actually define, in this case, domain would be what? 1, 6, well, and a monkey. Okay? That's the domain. The range is the set that has what? 2, -2, 8, and a piece of cheese. Is that okay? So that's what a relation is. A graph is a relation. I drew a circle earlier today. Here we go. Here's a circle. That circle is a relation because, well, it is a set of ordered pairs, right? So therefore it's a relation. So there's some kind of relationship between x and y. And actually here I know that that relationship is defined by that form. Okay? So actually the rule for the relation. But again, as long as it's a set of ordered pairs, we got ourselves a relation. Now we really here to study a special kind of a relation. We call it a function. Okay? So a definition of a function is a relation such that for every element in the domain, there is exactly one element in the range. So that kind of is weird. Another way, there is no repetition in the x value. So I cannot have two ordered pairs that share the same x value. That's what I'm trying to say. This is more kind of official mumbo jumbo. And the way we understand this, no repetition in the x value. So if I go back to my monkey cheese thing, I'll scroll it up in a second. I know somebody's still writing that. Was my original relation a function? The one that I wrote earlier? Okay, no, and why not?
Because one relates to a negative two.
That's right. So when I do those little graphs, I don't like to have that split. One cannot be relating to 2 and negative 2 at the same time. Okay? Kind of weird, but that's how we like it. I gave an example in my earlier class, because right as I was talking about this, I had a student who just got up and was packing and leaving, and I asked him, what's up? And he's like, well, I got to go to work. I was, oh, wait. I was like, well, aren't you in class? So he was not being a function, because he was trying to be in class and at work at the same time. So he was trying to split, literally, and he did. But that's all right. But that's the idea. So when we talk about functions, we don't like seeing that. So no 1x going to 2 different ones. All right? So we can actually see that graphically, and I'll do this in a second. Well, let me give you an example of a relation. And I'm not going to use monkeys a lot, so it's just to prove it. I don't know why I even did that. So if you were to pairs 1, 2, 3, 7, negative 1, 2, 5, 4. So here's a relation as a 4 ordered pair. First of all, what is the domain of this relation?
1, 3, negative 1, 5.
1, 3, negative 1, and 5. And again, you don't have to put them in order. You can if you want to, but you don't have to, because sets are in order. What is the range?
2, 7, 2, 4.
Now, do I need to list 2
7,
twice?
4.
2, 7, and 4, because we know that sets are repetition free. Now, is this a function? Yes. Even though there is a repetition in the y, we don't care, as long as there's no repetition in the x. Okay? So you can have 2 different x values going to the same, and let's say y values, I mean 2 different x values going to the same y value. It's like all of you, a bunch of different x values, converge in the same classroom. So that's kind of functioning. Okay? So that's the thing. So yes, it is a function. We can also judge whether something is a function by looking at its graph. Because we can always graph relations. Those are just sets of ordered pairs. And they're all going to be numerical, no monkeys. So we're just going to be able to graph them. So just by looking at the graphs, of relations and functions, if we have, let's say, just a straight line. So straight line is the set of ordered pairs that is a relation. Now, is this relation a function? So basically, you're looking for, are there any 2 ordered pairs, 2 different ordered pairs that share the same x value? And the answer is no. So it's good. It's a function. So yes, it is a function. No 2 ordered pairs share the same x value. Now, some of you know that there is a quick test that you can do by looking at the graph. What is it? Vertical line test. What you can do, you can visualize putting a bunch of vertical lines through the graph. And if each vertical line hits the graph at exactly 1 point, then you got yourself a function. So vertical line test. Okay? Now, at the same time, let's say if I look at a graph that we will call a parabola, Would that be a function? Yes. I put a bunch of vertical lines. Was that a question? Oh, good. So I put a bunch of vertical lines. We passed it. So yes. Bunch of vertical lines, 1 point, so that's a function. What if I push this parabola and, and it falls down and it looks like that now? Yeah, well, that's not a function. It's not a function. X is not, Y is not a function of X. That's really the proper term. So, not a function. How about circles? Any circles? No. Right? That should be pretty clear. If you take a circle, you're always going to hit 2 points or no points if you go outside the circle. So, is that okay? That kind of, again, most of you done functions before. I'm going to assume that you haven't. So we're starting functions from very beginning. Is that okay? How are we doing on time? I have about 10 minutes left. So I'm going to stop now. And you are